Hello, Chem 2. Welcome again to this week's installment of equilibrium calculations. So far, yesterday, we focused a lot on what the heck equilibrium was and a little bit about how to write our expression. So this is the objectives for chapter 12. You can see we've just barely scratched the surface of all the parts of equilibrium. Today is a deep dive into some of the math. It's the introductory part of the math. And then next week, we'll go very, very deep into applications of how to use this whole equilibrium concept. So today we're going to focus mostly on just being able to calculate the K, knowing what the Ks for other reactions are. We did that in the last video, but also talking about the different pressures and maybe there'll be one about talking about the original and the equilibrium partial pressure. So we're going to figure that out today. So administrative items, still the same things. You have the Chapter 11 exam to do if you haven't started already. Take care of that as quickly as possible. I think it's open until the 18th, if I'm not mistaken. And then Chapter 12, there is the optional AL, the required AL, and next week there will be the release of the test. Again, that you need to get a 75% or greater on the required AL before you can actually take the test. So chapter 12 is actually in your textbook is labeled as gaseous chemical equilibrium. Focuses almost exclusively in your textbook on Kp calculations. But my examples that I use that I've added to this PowerPoint is going to go back and forth between Kp and Kc throughout this chapter. But your textbook focuses almost only on gaseous. As a matter of fact, they call K, using the K for just gaseous equilibriums. So we've done the first two sections. We did not officially talk anything about the specific N2O4 to NO2 equilibrium. It'll be used a couple more times over in examples later on down the road, but we did not discuss it at all. Read the textbook if you want to get a little bit more into that, but they're just talking mostly about an example of a gaseous equilibrium that changes between a brown color and a clear color. We did yesterday, or in the last video, discuss equilibrium constant expressions. So today we're going to figure out how to determine what the K value is, or the Kp or the Kc from data. So K can be determined if you have partial pressures of your products and reactants. So suppose you know what those numbers are. You know that once the system has reached equilibrium, you know the values for the K, for the equilibrium pressures. All you have to do is plug the numbers back in. They talk about ways that you can use the data here as being the equilibrium partial pressures can be used directly to get K. And maybe I'm going to show you an example a little bit later on of how you can use original partial pressures and changes that you know will take place in order to determine the K. And hopefully the few examples I use on this video will help. This is a little bit of a lengthier video because it is the first one to dig deep into stoichiometry and the calculations. So the next couple, this one plus the next, I think the next two, will be a little longer and have more examples than normal. But just bear with me. And again, you can always pause anytime along the video, take a break, and then dive back in to get you additional information. Something you can't do in class, which probably some of you guys wish you could. Okay, so example number 12.3 in your textbook talks about this ammonium chloride reaction. Ammonium chloride, which is a solid, is sometimes used as a flux in soldering because it decomposes into heating, meaning it'll break down into two gaseous components, ammonia, and hydrochloric acid, or HCl fumes. So both of those in this situation are gases when this material is heated excessively. The HCl is what removes oxides from metals so that you can cleanly solder. That's why that was thrown in there. So at a temperature, I know that if I take 12.6 grams of the ammonium chloride and I allow it to decompose completely, when the system reaches equilibrium, the pressure of the ammonia is going to be 2.5 and the pressure of the hydrogen chloride is going to be 4.8. Both of these are measured in atmospheres. This question asks you to calculate the Kp for this reaction at that 400 degrees. So all you need to do since you have the pressures at equilibrium, and how do I know it's the equilibrium? Notice here on the slide, it says directly, and again, I'm going to pull out my pen, it says directly, in a certain equilibrium system. It means it's at equilibrium. This is what's going on. These are the conditions that are happening at equilibrium. Looking for those context clues, but this is indicating directly that all these numbers you have are at equilibrium. So we're going to use them. So you have your equilibrium expression. The first thing you need to do is, so you have an equilibrium equation, you have to write your expression. So in this situation, pretty straightforward. The Kp is going to be the pressure of the ammonia times the pressure of the hydrogen chloride, both raised to the first power because they both have a 1 in front of as this coefficient. And it's going to be over 1 because that solid, the hydrogen ammonium chloride, is a solid, so you do not have that included in the equilibrium expression. Then all you have to do, honestly, is just plug those numbers in that you were given. 2.5 atmospheres times 4.8 atmospheres, multiply them together and get 12. That's it. If you have the numbers given to you at equilibrium, there's nothing more than plugging the numbers into the expression that you would have to write. Take the values you were given, especially if they say, like this slide did, that the numbers are at equilibrium. Just take those at equilibrium values and put them into the expression. That's pretty straightforward. Okay. They make a note here that, notice we did nothing with that 22.6 grams of ammonium chloride because it's not part of the equation. It's not part of the expression. It's valuable information, and we'll see when we get a little bit deeper into the next phase as to how that solid amount does matter. But as far as doing what they're asking you to do in this situation, that's just an irrelevant piece of information that is not necessary at all in this calculation. Okay, let's look at another example. Here's another equilibrium. It says that you have this equilibrium. Again, they're all gases. You notice they're all gases. There's no solids and no liquids in this one. And originally, and again, that's not at equilibrium. Originally, it only contained hydrogen iodide. And the pressure of hydrogen iodide, the compound over here, was just 1 atmosphere. That's it. And then it went to equilibrium. It tended to shift in a way that you started to make some H2 and I2, while at the same time remaking the HI until it reaches equilibrium. Okay, the question is, what's the pressures of I2 and H2, so I2 and HI at equilibrium if, and here's the key here that help you out here, that at equilibrium, once it finally does reach equilibrium, the hydrogen pressure is going to be 0.1 atmospheres. Okay, so you've got a lot of information here. You've got original, and you've got some information, a little bit of information at equilibrium, and we want to link it all together. And we're going to do that using a technique called an ice chart. So here's the information you have. You know the initial pressure for the HI. You know the final pressure, the equilibrium pressure for H2. You can imply that the initial pressure for hydrogen and iodine are both 0 initially. And the reason why we can do that is because they don't mention it at all. We can assume that the pressures of those two are 0. If for some reason they say, and you add some quantity of, and they don't tell you what it is, you can't make that assumption. But since they said nothing about the pressure of hydrogen and the pressure of iodine, you can assume that it's just 0. And then you know what they're asking for, the iodine and the HI. So, strategy. First thing we're going to do is create what's called an ice chart. Now, an ice chart is a way of organizing the information we're given into different facets. And here's what an ice chart looks like. Now, ice stands for I is initial. It's the initial set of conditions. C is the change. Change is how does the initial set of conditions change in order to get to the E condition, which is equilibrium. We could have used this same chart mentality in stoichiometry a couple units back, and in that case it would be initial change and ending. But now we're talking about equilibrium, which is the same thing. It's when this reaction has come to an equilibrium, has stopped changing. What's the equilibrium conditions? Now, we're going to deal with pressures. So we know that of what was given to us, we were given that our initial hydrogen iodide was 1. And we implied that the initial amounts of hydrogen and iodine were 0. Other piece of information was given to us was that our ending pressure, our equilibrium pressure of hydrogen was 0.1. So the question is, how did things change? Well, here's the way this table works. There's two things involved, two really, really cool things. In order to go from initial set of conditions to the equilibrium, the change has to take place. So if I look at this hydrogen, I know that it started off as 0 and it ended up as 0.1. I know this sounds kind of ridiculous, but that just means we added 0.1 atmospheres of pressure. That was the change. The change was a plus of a 0.1. A way we can kind of collect our thoughts is to take our ice chart and start looking at the different changes that take place and try to put the pieces together. Okay, so since we know that the initial pressure was 0 and it ended up at 0.1, we know that that's the change. That change in pressure of the hydrogen gas was a positive 0.1. And the thing you'll hear me say time and time again is I plus C equals E. I, the initial conditions, plus C, the change, is equal to the E, the equilibrium conditions. I plus C equals E. So what we're going to use is we're going to use a little bit of algebra just to help us keep track of variables and such. And you'll notice that if I look at the equation and being a dividing line between products and reactants, on one side of the reaction, the numbers are going to go up. On the other side of the reaction, the numbers are going to go down. In this situation, it's very, very easy on twofold to realize that this right-hand side has to be the pluses. And the two ways to do that is, one, we saw that hydrogen went from 0 up to 0.1. That means it increased. So that means everything on the right-hand side, everything over here, has to increase, has to be the pluses. And everything on the opposite side of the equilibrium sign has to be a minus, has to go down. One side goes up, the other side goes down, kind of like a seesaw. Okay, the other thing in here is the coefficients. Use x's to help you figure out what those are. But notice that since there are 2 hydrogen iodides and only 1 hydrogen and 1 iodine, that there's going to be a stoichiometric relationship that's going to make things a little more cumbersome. So we have to worry about the coefficients in the reaction to figure out those ratios. So we had that there are 2 HIs for every 1 H2, and there's only 1 I2 for every 1 H2. So there is a stoichiometric relationship that allows us to make sure that not only we have the signs on the right side, but we have to put the right number out in front of the x's. So 2 on the left-hand side, 1 on the right-hand side. And lastly, since we know that 0 plus what equals 0.1, we know that x happens to be 0.1. If x is 0.1, then I'm going to add 0.1 over here to the iodine. I'm going to add the 0.1 there, and I'm going to subtract 2 times the 0.1 from this side. And I'm going to get a relationship, again, I plus C equals E. The initial set of conditions plus the change equals the equilibrium conditions, and I'm able to make the connect calculations. I'm going to fill in the rest of the rows by saying, well, I know that 0 plus 0.1 is 0.1. And I know that 0.1 minus 2 times 0.1, or minus 0.2, is 0.8. Those are my pressures at equilibrium. The hydrogen iodide's pressure is 0.8, and the iodine's pressure is 0.1. Now, this question could have taken one more step and said something along the lines of, and then calculate the Kp value for this equilibrium, in which case we would have just plugged the numbers in just like we did in our previous example. Okay, let's move on to another example that shows how you can incorporate the equations and all this equilibrium stuff. So they talk about here very quickly, sorry, this one slide. As the system approaches equilibrium, the changes in the reactions and products are related to one another through the coefficients, and we saw that. Okay, so here's an example. Now this one's going to take a neat little twist and incorporation into other units that we've done in this class. Okay, so we are going to take a mixture of carbon dioxide, hydrogen, and water and put them into a container. Now notice, here's the equilibrium that's going to take place, and we're going to add carbon dioxide, we're going to add hydrogen, and we're going to add water. And we're not going to add any carbon monoxide. I want to make sure that's clear. We're going to add some number of moles each to each one of these. And then the last thing that it said, that gave you as far as the equilibrium goes, is then the equilibrium is established, it kicks in, and when we're done, the new pressure of the water is 3.5 atmospheres. Now, let's look at this for a second. They didn't give you any pressures to begin with. They gave you moles. They gave you a number of moles of each one of the materials. They did not give you pressures. They gave you pressures, they gave you volume, they gave you temperature. Yep, we're going to be using PV equals nRT in order to determine the pressure. We're going to be using our ideal gas law to find out what those pressures were in the initial set of conditions in the reaction. And then they want us to calculate the partial pressures of all the components at equilibrium and then calculate the Kp. Like I said in the last example, they could have taken it one step further by plugging the numbers in once you get them. So let's see what we got. So ice chart, initial set of conditions, I have everything in moles. Now here's one facet or one concept about the ice chart. You can use 3 different units in your ice chart. You can either do everything in moles, everything in pressures, make sure they're the same units of pressure, preferably atmospheres since we're doing equilibrium, or everything in concentration. To make life easier in this situation, since it's asking for a Kp, I want my chart to not be in moles. We could do that. It would just make things a little more cumbersome with the amount of calculations you would have to do. But I want to go ahead and change everything over into pressures by using the ideal gas law. So I'm going to take these 3 different numbers of moles that I was given, and I am going to change all those moles over to pressure by using the ideal gas law, PV equals nRT. So I'm going to take nRT divided by V. The number of moles was given to you for each of the substances. You're going to use the R that's associated with atmospheres because in order to use the Kp value, everything has to be in atmospheres. You're going to use the T, it was given to you as 500 K, and the volume was given to you as 2 liters. You're going to do the math 3 times over. Now, all your units here have 3 sig figs because of that 500 K. Might have been able to measure that a little more accurately to get a little better number, maybe to 1 digit past the decimal, but that didn't happen. So we're going to use 3 sig figs for each. So we know these are all the initial sets of conditions. We either know the initial pressure of carbon dioxide, the initial pressure of hydrogen, and initial pressure of water. So we essentially are exactly where we were on the previous example, where we had the initial sets of conditions. And, little twist here, the other piece of information that was given to you in the problem was much like the last problem. They gave you the amount of water that was established at equilibrium of 3.51 atmospheres. Now, so we have to put in the changes. On the right-hand side, we're going to put the pluses. Left-hand side, put the minuses. There's 2 reasons you know that. One, you know that 3.28 becoming 3.51 is an add, is an addition. So that means the right-hand side is going to be a plus. The other thing is, it's a huge help, is whenever you have a 0 as one of your components, at equilibrium, all components must be present. I know that may not have been extremely obvious from the previous videos, but let's think about it. In order for a reaction to go forward, both / all reactants have to be present. In order for reaction to go backwards, both / all products have to be present. So in order for a system to be at equilibrium, all components, reactants, and products have to be present. So we're going to have make sure everything's there. Whenever you see a 0, like we have here at the carbon monoxide, that is a dead giveaway that side is going to get the plus, and then you put your coefficients out front. It happens to be for this reaction, all the coefficients for 1s. So now we have our initial 3.28 for the water. we have our final for the water, 3.51. We know that I plus C equals E, so we can do the math and find out that what X is. X is the difference between the final set of conditions and the initial set of conditions, or 0.23. So we're going to add 0.23 to the carbon monoxide and subtract 0.23 from each of the other two components. So we get 0.23 as being my pressure of my carbon monoxide, 1.82 being the pressure of my hydrogen, and 3.87 being the pressure of my carbon dioxide. So I essentially have done the math of adding or subtracting the 0.23 to my initial sets of conditions. I now have the pressure of the carbon dioxide, the pressure of the hydrogen, and the pressure of the carbon monoxide, as was asked in the question. Now it's time to find out what your value is. That's just as simple as taking the expression and plugging the numbers in. And I find that the value of my expression to 2 sig figs, because that 0.23 for the carbon monoxide is 0.11. Okay, so in our 3 examples we've done, we went from I have the numbers, put it in, I have initial sets of conditions and one of the final set of conditions, do the math, and then bringing it all together. Add a little ideal gas law in for good measure, because we can't forget about those past units. Okay, last example. We're at like 22 minutes now. We're going to look at the last example. Last example of this video looks at another example of a expression. However, the twist here is that in this situation, I know what the Kp is. I know what the Kp is. I know at equilibrium, I know what 2 of the components pressures are. And it's asking me what's the last component's pressure. Okay, so I know what my Kp is. I know what my pressures are for 2 of the 3 components. And it's simply asking me what is the pressure of my last component. Well, if that's my expression, that's my equation, and that's my expression, but the one that I need to solve for is this one right here, the pressure of the chlorine. So I'm going to manipulate this equation so that I get pressure of the chlorine by itself. Pressure of the chlorine equals the Kp times the KSO2Cl2 divided by the pressure of the SO2. So what I've done is I've divided both sides by pressure of SO2, and I've multiplied both sides by the pressure of SO2Cl2. And lo and behold, at that point, in order to get the pressure of the chlorine, I have all these other numbers. I just got to plug them in and get an answer and find out that my pressure at equilibrium, if my Kp is 2.39, and my pressure of my SO2Cl2 is 3.31, and my pressure of SO2 is 1.59, then my pressure at equilibrium for my chlorine would be 4.98 atmospheres. Okay, so just more ways to look at the manipulating of the equation and to use all the stuff at equilibrium. What's next? Well, what we're going to do next week is we're going to dive very, very deep into how to use the KEQ expression, whether it be the Kc or the Kp, and we're going to spend a lot of time thoroughly investigating how to use I plus C equals E and how those equilibrium concentrations can link up to the Kp value or the Kc value, and just look at a whole lot of examples and all the kind of cool things you can do with this to be able to determine anything about a system at equilibrium, or maybe even what the conditions were at the beginning if we know what the equilibrium is in the end. Anyway, that's the end of this video. This is the last one of the week. Hopefully everybody is being safe and healthy and is practicing their social distancing. I am very saddened to know that I will not be seeing you guys at all this year except for via Teams. We need to have one of those days where you guys actually make yourself presentable enough to show yourselves on the screens, because I miss seeing your smiling faces. This new way of teaching is really, really weird. So everybody have a great day. Always remember, never forget, you know this phrase that pays, sig figs really do matter. Toodles.